Hi, my name is Savannah Coper, and today I'll be presenting a wrist-worn device used to detect hand gestures. Augmented and virtual reality technologies are often viewed as the next generation of smartphones and tablets, and they introduce entirely new forms of interaction with the digital world and with robotic technologies. In particular, augmented reality has the potential to completely transform the way we interact with real-life objects, especially in fields that require manual interaction like medicine, manufacturing, and human-robot interaction. We want to enable users to tangibly interact with real-life objects like touchscreens, cups, medical equipment, and robotic manipulators. Unfortunately, currently available technologies on the market rely on handheld controllers, which completely block tactile interactions. That might be fine for closed-off virtual reality, but for mixed reality and robotic applications, we need a hands-free device. Current research aims to develop a wearable approach to touch and grasp detection, but faces several key limitations. Inertial measurement sensing has good generalizability, but is limited by low touch detection accuracy without placing IMUs directly on the fingertips. Computer vision is another hands-free approach, but also struggles with low detection accuracy and is limited by camera occlusion. Finally, electromyography, or EMG, can be used to classify a wide range of large, mid-air gestures, but robustness is limited by the need for direct skin contact with the sensors. In our work, we aim to address the unmet need of hands-free gesture detection by designing a wrist-worn device that combines a dense network of near-infrared optical emitter and detector pairs and a 6 degree of freedom IMU. We hypothesize that the generalizability of IMU motion sensing will be able to complement the precision of optical sensing for touch detection. The near-infrared light is able to penetrate the skin deeper than visible light and can detect subtle changes in blood flow and tendon position depending on hand movement. So today we'll be presenting a 3-step approach. First, we determined which touch gestures to test. Second, we formulated our dataset through conducting an in-lab human subjects test. And third, we used a machine learning approach to predict gestures from the wrist-worn dataset. So let's start with step 1, our touch gesture set. As you can see in these videos, we typically interact with our phones and tablets using surface touch gestures. Previous research methods have been successful at detecting large-scale mid-air gestures, but there hasn't been much work in detecting these small touch microgestures. We also wanted to see if we could detect when a user picks up and releases a standard cylindrical object. So this could represent a tool, a robotic manipulator, or a passive haptic object. Moving on to step 2, we conducted a human subject study with a diverse set of 12 participants. Each participant conducted a set of touch detection tasks while wearing the wrist-worn device, and a copper mesh and contact pad to collect the ground truth data. Participants also completed grasping tasks of various time durations, both with static grasps and picking up and moving a standard cylindrical object. Now let's take a look at the raw optical data coming out of the wristband with respect to time. As you can see here, each gesture has a unique signal profile. This allows us to map each interaction gesture to the ground truth data and create predictions using the wristband alone. Now, it might be a little hard to interpret just by looking at it, which is why we need step 3, the machine learning pipeline. This here is a big overview of our machine learning algorithm, which basically serves to map all of this wrist-worn data to ground truth data. Now let's take a look at the first step, the raw input data from the wristband. We found that NIR sensing is uniquely effective for detecting contact versus no contact with the surface, since small micro gestures involving surface contact can easily be seen in the blood flow and tendon movement of the wrist. As you can see from the chart, NIR optical sensing as input had the highest performance after pre-processing. Next, we compared 7 published time series machine learning algorithms and found that a 1D CNN yielded high prediction accuracy. We optimized over a number of hyperparameters, including model depth, kernel size, windowing size, and calibration time. After predicting when the contact event occurs, we can use these results to parse out contact events for classification purposes. All we are detecting in this stage is whether the finger is in contact with the surface or not. While the optical sensors were effective at detecting this small-scale surface contact, the IMU sensor was able to most accurately classify the directionality of swipe and scroll gestures. This here may be due to the generalizability of the IMU data, which allowed us to train on data from all users rather than retraining for each individual user. Based on these results, we found that a 2-level hierarchical neural network yielded particularly good results, where the first level uses optical sensing for event detection. And once events are detected, we can conduct classification at the second level of the network using IMU sensing. This means that the combination of NIR plus IMU sensing can be more effective than just one alone, since they contribute to event detection and direction classification, respectively. Using this framework, we were able to achieve greater than 95% accuracy for all 5 basic touch interaction gestures, including tap, hold, swipe, scroll, and zoom gestures. We aim to minimize both false positives and false negatives in our results. We also classified directionality within swipe, scroll, and zoom gestures with an average of 96% classification accuracy, and classifying between all 5 input gesture types resulted in an average of 90% classification accuracy. Finally, for the grasp detection task, we wanted to find when the onset and offset time of the grasp was in order to determine exactly when the user picks up and lets go of an object. Overall, we were able to achieve 98% grasp event detection accuracy, with a relatively small error regarding the timing of the grasp onset and offset. So our biggest positive takeaway here is that our detection accuracy meets or exceeds that of existing literature. And some other advantages to our approach are that the wrist-worn form factor allows for complete freehand movement, and that IMU and NIR sensing do not depend on skin surface contact and are robust to camera occlusion. But on the other hand, our study did not include as broad of a grasp gesture set as some existing literature, and we also didn't interview our participants for human usability information. Both of these limitations we hope to address in future work. This coming fall and winter, we plan to conduct further tests that involve developing a multi-user model with a larger number of users. We also plan to investigate the performance trade-off between prediction latency and accuracy. And finally, collect qualitative performance metrics to make sure that we are designing this whole system with the user in mind. Thank you so much for listening, and I'd also like to thank Stanford, the Knight-Hennessy Fellowship, and the NSF Fellowship for sponsoring this work.